ما ريكورد؟
أي نعم.
تمام. Mr. Bilal, are you there? Mr.
Yes,
Bilal?
I'm here. Can see me, right?
Okay. Yes, now we can see you. Okay, nice to meet you. So I believe right now we have like the average attendees sufficient. Okay, I believe they will increase slowly. Okay, and what we will do, we'll make a small introduction, okay, about the lecture, okay, like about small talk, then like about three, four presentation from our organization, and we'll keep the floors for you afterward, okay, and we kindly request to close the camera just for the lecture, okay, for the tutors, keep it open. So if anybody open its camera, we'll kindly request to close it. Okay, with this to affect the recording. Thank you, Sufyan. So, dear all, I would like to welcome you all to our webinar number 3 in 2026 regarding Weatherford Pulsed-Neutron logging application. Will be presented by Mr. Bilal Shaheed from Weatherford company. My name is Mazen Al-Hilali. I'm a senior petrophysicist with the Westcon 2 project in Basra, Iraq. We have a little bit pause this year with our webinar due to the current situation, as you know, with the war and the Strait of Hormuz. Hopefully, we'll start to back doing the usual webinars, monthly webinars, okay, because we have to schedule everything for the last few months. I will keep the floor right now for Dr. Mohammed, our VP of Technology with SPWLA Iraq. Dr. Mohammed.
Thank you, Mr. Mazen. Dear attendees, good day. It's my pleasure to welcome to you today's session organized by SPWLA Iraq. My name is Mohammed Jawad Zainul Abedin, and I serve as the VP of for SPWLA Iraq. I hold a PhD in petroleum engineering, and I am a senior faculty member at the University of Kirkuk. We are honored to host the third webinar of the 2026 SPWLA Iraq webinar series. Today's presentation is titled Weatherford Pulsed-Neutron Tool Theory and Applications. The session will be delivered by Mr. Bilal Shaheed from Weatherford. Mr. Bilal Shaheed, welcome and thank you for joining us. Dear distinguished attendees, we kindly ask you to note the following important points. Please keep your camera and microphone turned off throughout the webinar. The session is being recorded. If you have any questions, please type them in the chat box. The speaker will answer them during the question and answer session at the end of the presentation. Additionally, a link to join the SPWLA Iraq community on LinkedIn will be shared in the chat box during the session. Thank you for your attention and participation. Mr. Mazen, the floor is yours.
Thank you, Dr. Mohammed. Mr. Bilal, just I will share my screen for very quick presentation. Okay. Yes, thank you so much. Okay. Dr. Mohammed, you can see my screen?
Yes, Mr. Mazen.
Okay, so they're all welcome again to our monthly webinar. This is the third one. Unfortunately, as we have mentioned, we have to reduce the number of webinar for this year. And I like to welcome you again along with Mr. Bilal Shaheed for his volunteering work with the Society of Petrophysicists. As we have mentioned, this webinar or the theme for this year will be all focused on pulse neutron from tool manufacturer and from software company, and we'll try also from operator side. This webinar will be sponsored by Weatherford, represented by Mr. Bilal Shaheed. which will give this lecture. We have managed to make 3. This is the 3rd webinar. Hopefully, we can make at least 5 or 6 webinars before the year closing. The next compare one with Kappa. Okay, with Kappa, how to analyze the post-neutron data using Emerald software. And I really appreciate all our sponsors from different companies. As usual, every year, if anyone attends 6 of our webinar, maybe we'll reduce this number this year. Maybe we'll make it 4 or something. Will be awarded a special learner certificate in December 2026. And everybody is welcome to join Iraq chapter officially through SPWLA.org. Even we are providing all our webinar free for everyone, member or not member. Question and answer will be kindly kept at the end of lecture. You can write your question at the chat box. Okay, I'll try to be answered later. I will leave the floor to Mr. Bilal. Okay, and Mr. Bilal, he's a team leader with Weatherford. He with holding a bachelor and master degree from in petroleum engineering, and he can introduce himself better than me. Thank you all, Mr. Bilal. The floor is yours.
Thank you, Mazen team. As Mr. Mazen was mentioning, yes, my name is Bilal Shaheed, and I'm originally from Iraq. I've been in Weatherford more than 15 years already. I've been working in Iraq in the beginning. Now I joined Oman for the past few years. I work I actually have a degree in master degree in petroleum engineering. I've been working in open hole and case hole, mainly open hole actually, with the astrophysical analysis and image interpretation, and also partially for like a pulse-neutron evaluation. So today will be actually more of a learning session. We will be learning from each other. So you can ask your questions, and I'll try to answer at the end, inshallah. So Raptor tool, or the CRE, which is the case hole reservoir evaluation tool, as it is known, which we are mainly used for the pulse-neutron or let's say case hole saturation to get the oil saturation. So why did we invent this tool? Why it was invented, I mean, as a service, let's say. The challenge is to see the saturation over the time. So we know that once the well is drilled, we will be, I mean, we have the wireline or the LWD to be in touch with the formation and get the evaluation immediately. So we can see that formation. We can get in touch with it immediately, I mean, directly. However, over time, when the casing is there, the cement is there, it is a bit of challenge. So after a few years of production, we will be having the challenge of knowing the new saturation or the updated saturation at this moment. So this tool was invented for the service to get the updated saturation, let's say, and the contacts, the oil-water contact or oil-gas contact, and so on. So what the solution here is the Raptor case hole reservoir evaluation system. It can see like the barriers where we have the cement, the casing and cement, and even if we have a double barrier, like if we have double casing, or even with the tubing, so we can even see the formation and we can get to the saturation of that area or that zone. So we can quantify it with high accuracy, and we can also compare it to the open hole, and we can see the updates. There are in this tool we have 3 measurements, and 4 detectors. We'll go to these details later, inshallah. So what is the benefits? Why should I use this tool? So it is, you can see what you have in your reservoir. It can save your money with high accuracy professional interval by knowing your updated saturation and the updated contacts. You can increase your reservoir life, especially like you have more of the monitoring. You can see like you can control your gas presence, your oil, your water, your aquifer. So all of that can be controlled by knowing the saturation or the fluid contact from this tool. You can avoid the remedial cost from water production. Of course, this is very familiar issue for all of the operating companies. Identify the producing zones missed by open hole logs sometimes. Confirm the hydrocarbon potential before completion. So we can know how much oil left and what is the potential of this area. So here is the agenda for this presentation. First of all, we will go to the specifications of this tool, the modes that we are using, what does every mode means. Then we go, let's just a short session for physics, just for those who are interested to know the physics behind this tool. We'll talk about the new, let's say, the update Raptor tool, the updates that we have in the Raptor tool, the applications that we have, some of the case studies that are more suitable to our, let's say, area in the Middle East and specifically to Iraq, and something about production optimization later at the end. So what is Raptor? It is a formation evaluation tool that can measure your formation and the fluids inside the casing. So you can see it behind the casing. It has 3 modes actually. These 3 modes, as we know, the Sigma and CO, which are very common. We have the 3rd mode, which is only particular for this tool. We call it Envision. We will talk about it in details later. When we say Raptor, it's not just a tool. It is a full system, which is a complex, let's say, it is fit to a complex environment. It's fit to, like it has some special calibration system. Also, the modeling is some specific model that we can use for for every particular environment. So all of that will be, we will talk in details in the next few slides. So here are the summary of the system of this tool, or let's say this Raptor as a system. So we have, as a tool, we have 5 detectors, which is the only one that comes with 5 detectors. 4 of them are actually gamma ray detectors, which we use are the Langston bromide. So this is the special about it. We will give more details about what the special details about this detector. The good thing about having 4 detectors, it will increase the sensitivity of gas. So using the conventional tool, or let's say the traditional 2 or 3 detectors, will give us better estimation of oil. However, when we move to gas, especially in tight zones, it's better to go further. So that's why this detector was invented, to see more gas, which can increase the sensitivity to 200%. So we will see that also in some of the drawings there. The calibration system also, it is special that we are using like 3-point calibrator. We will see it also. So that will give us more precise measurements and high quality. The characterization or the modeling, so for every particular environment or let's say, schematic that we have, either it is double casing or with the tubing or whatever, even the borehole size, even with the high borehole size, we can characterize that or model it to be able to have a more precise or more accurate measurement at the end. So all of that will give us a better and better estimation for the reservoir and better estimation for our saturation. So here are just a few, just to summarize that, very small comparison between the standard pulse-neutron and the multi-detector pulse-neutron here. So we are using here the 5 detectors. It has, like, because of, this is just a cartoon drawing showing. Let me get the laser. Now we have like a source, and these are the detectors. So by having these 4 gamma ray detectors, the orange ones, we can have 6 ratios of the multiple investigation volumes into the formation. So by having that, we'll get better estimation and better, let's say, single to noise ratio also. And that by that we will have better estimation of our reservoir. It has capture and elastic capabilities. The modeling that we are using is the Monte Carlo modeling, which is specific for this tool. To give it specific actually results for every environment. We are using 3 modes, as we mentioned, like sigma, CO, and the gas, which we call it Envision. We can flask the tool actually when we are running in a high temp environment. So we will see some examples later, and the specification as well. There are also, we can include another gamma ray in the tool string that will give us, we can measure the silica activation, especially when in the gravel. For example, if we have a gravel back in the logging system there, we can use it as well. So here is the comparison actually between the Raptor. It's actually the normal Raptor and the Raptor with the high temperature. So this is actually comes with the flask. So you can see the difference actually is in the temperature here. So this can go up to 260 degrees. So especially when you are like here in the Middle East, especially in Oman, we are having many fields, or let's say that has like heavy oil. So they need to drill 2 horizontal wells on top of each other. By having these 2, like they inject steam in one of them, and then from the one below, they get this oil to be little bit heated, so it can easily produced. In order to measure, like to have this tool in this environment, you need, it's not all of the tools can go in, especially for the, because we have very high temperature there. So by having the tool flask, we can run that tool. So the side, the diameter is around 111/16, which is 1.69 standard size for the normal one, but for the high temp, which comes with the sleeve, with the flask, so it is a little bit higher. The length is a little bit increase when we have the high temp one because of the telemetry. Actually, the depth of investigation, actually, this is related to the physics. So I believe it's because, I can think about it if, like when you have a gun and you take a bullet out of it, you will have a shield in front of you. So you will not be exceeding that shield. So when it is there, that's it. So you cannot reach beyond that. So this depends on the type of interaction. So since we have a capture which can go beyond the size of, let's say, the inelastic, so you can see it's, let's say, as an average from 5, let's say, to 15 inch as an average. So this is the depth of investigation. So here is the tool. We have like a generator, which we generate the neutron here, and then we have detectors. We call it proximal, near, far, and long. The old tools comes only with the near and far, the old ones, the traditional ones. However, we have 4 now, and this is we call it a fast neutron. We'll talk about it in the next slide. So by having 4 detectors, we can have 6 ratios. So this 6 ratios will help us to increase our signal to noise ratio. So we'll have better, let's say, a view to our reservoir. We can have a capture and analytic capabilities and a spectroscopy for each of one of them. Like by having this far detector, we can see the gas by better sensitivity by 250% better than having the traditional ones, like even with the proximal and far. We will see the comparison in one of the slides later. So why did we use the lanthanum bromide? We mentioned that we are using that. So actually, even the new, let's say, competitors, they are, and their new tools, they are using same as this detector. So they used to use these detectors before. However, now they move to this one because it is more, let's say, efficient. How? So it is 3 times greater peak than the old one, like the BGO. So the peaks give us better resolution to and better measurement. 10 times brighter. So when you have more brightness, you get better reading of your signal. So that will enhance your signal and to decrease your noise in the measurement. For the temperature stability, we are much better than the older ones. So you can see it's 30 times better. And that's will it will help you to not lose your signal by having higher temperature. Now the fast neutron. So what is it for? Actually, this will not enter as a measurement for the let's say the sigma or CO or the gas. It's mainly made to understand the neutron emission rate, to see how its pulse, the data timing, accuracy. All of that will help us in the characterization actually for the tool with the formation that we have. So it is mainly to remember that it is used for the characterization and for modeling. The calibration system. So we mentioned that we have a special calibration system. So usually the older ones to have only one tank to put the tool in, which is full of water, and that will calibrate your tool, which is okay. However, here we are having 3 points. You can see there are 3 holes here, and the tank is full of water. So the first one here for hole, you can see this hole is a little bit higher in diameter. So that's why it's used for gas, and the lower one for oil. So by calibrating all of the 4 detectors in these 3 points, you get more efficient reading and let's say we call it multi-point oil and gas sensitivity calibration. So that will give us better performance for the logging. Now is the technique. So what are the differences? Like we know that sigma carbon oxygen, but the envision also we need to know about it more. However, I will also just to refresh your minds about these 2 conventional measurements. So what is the sigma actually? So we can get the measurement for oil, gas, and water, and by having a speed of 5 to 6 meter per minute, which is considered to be a higher speed actually, we can get only 1 main and repeat pass. However, this one is salinity dependent, so we need to have a higher salinity, and we should know it as well. So by knowing the salinity and We know it's very high. We'll show a diagram later how to decide which mode to use and which one is better for our, let's say, environment. So the sigma, it's like a signature for the area. Like you can have your like sigma value for each elements, for the oil, for the gas, for the water. However, for the fresh water, it will be similar to oil, so it cannot be used in the fresh water, or it can help only to when we log it with CO to define these areas of the fresh water. So we can see some of the examples later in the case studies. Now carbon oxygen. So carbon oxygen mainly to see, let's say, the difference between the oil and water. And the physics behind that, we'll see it in the next few slides. And the good thing about it, this is independent of salinity. So if you have a formation and you don't know your water salinity there, so this is the good, this good option to run in your reservoir. And that will differentiate between oil and water here. We can always run it with at least 3 passes. We can go up to 5, which is getting better to enhance your statistics. Also, the logging speed is very low compared to sigma. However, it is high because we are using this kind of detectors, which are having very good decay rates. So that's why we are using this speed, which is better than the other, let's say, detectors type. So 1 to 1.5 is a good speed actually for CO. Now the Envision. So this one, to quantify gas. We said like we have the fourth detector, the further detector, which can see the gas, because when you have neutrons in the gas environment, they will go further in the formation. So to detect the interactions, you need to have a higher, or let's say a further detector, and that's why this tool, this mode was invented. So is it CO or is it sigma? No, let's say I could say it's a combination of inelastic and a capture, which is the niche of this tool, that we have in a certain way to measure the gas. So the good thing, we can go up to 3 meters per minute as a speed, which is better than the CO, and we don't need to have, multiple passes. So main and repeat will be enough to measure. And the good thing, it's salinity and porosity independent. So the CO is somehow we need to have a little bit higher in the porosity to measure it. However, for the Envision, we can go even very tight reservoir and we can still measure the gas there. So this is the one that I was talking about, the application chart, or this is, let's say, as you can use it as a reference to know which mode you choose for your reservoir. So if you have a porosity higher than almost, let's say, higher than 20 and above, 20% and above, and a salinity, let's say, around more than 100K, okay, so in this case, you can use sigma. However, if you don't know the salinity, or you have very low salinity and your porosity is above 15%, so CO is a good option as well. However, for the Envision, you can use it even above, like porosity up, down to 3%. So even if you have very tight reservoir with 3% porosity, you can still use the Envision with the gas and you can't see the saturation. So these are just fields in the world that are having this environment. So we have done jobs around the globe. So this is the comparison actually between having only 3 detectors or having 4 detectors. So why do we need to run the tool in the beginning? We said we need to run it to see the saturation. Okay. And to know the saturation, actually, you need to have a good sensitivity. What do I mean by sensitivity? Is the difference between the gas line or let's say the hydrocarbon line in case in the oil CO. But here this is for the Envision. So the difference between the gas line and the water line. Okay, so if you have a big difference or let's say a high difference, so you have a good certainty in your measurement. So imagine like your data is here. So you know the difference between here and there, so you can calculate your saturation based on that. However, if you have your, let's say the traditional one between the 3 detectors, so let's say this one and the far one, proximal we call it, and the far. So you have this much of difference. So you will, in case your data is here, you have higher uncertainty compared to this one. So here you have better, let's say, confident of your measurement than in here. So this is when we are talking about 20% of porosity. Imagine you have a very low porosity, like in here, 5%. So the difference will be even tighter. So that's why having 5, let's say 4 detectors and a further detector in particular is better. So that will increase your certainty or let's say sensitivity by 200% or even going to 250%. So when compared to proximal with the long and the proximal with the far, as of the traditional tools. So here we are going back to the physics. So I know this is a little bit looks complicated, but we will go one by one. So this is the, let's say, the life of the neutron. So we have a generator here. You can see it. By this generator, we are, let's say, creating these neutrons. We are emitting these neutrons, however, but in a very high speed. Not like the open hole neutron tool. This is done naturally here. We are creating them. So by pushing a button, we make this neutron. So it is safe to see it in the ground. So there is no, let's say, it is not radioactive. However, when you switch it on, I mean, it will be crazy. Of course, everybody will be in danger unless it is in the tank. So what happens? Why it is in danger? So when we create the neutrons, let's talk first how we create the neutrons. So you have 2, let's say this is the isotopes of hydrogen, or what we call like deuterium and tritium. So you have the deuterium 1 proton with 1 neutron, and the tritium comes with the 1 proton and 2 neutrons. So we accelerate this one because this is smaller in size compared to the tritium. So, and it is less, let's say, less mass or weight. So by accelerating this one, the deuterium, to hit the tritium, there is this where the nuclear fusion happens. So what will happen? We will end up with alpha particle, which is after the, I mean, stabilizing, it will become a helium, and then we will emit 1 neutron. So the actually the mass part of it will be transferred to energy, and that energy will be transmitted to the neutron. So that's why we have very high speed neutron. So it comes with 14 mega electron volt. So this is, by the way, very high speed. The thermal one, which is the neutron that comes, after a few collisions, it will reach to a thermal energy, which is only 0.025 electron volt. So that's kiloelectron. So it will be, this one is very high speed. So that's why it's very dangerous. So what are the interactions that will happen? We have something called inelastic scattering, we have capture, we have activation, and there is elastic. So the elastic actually just like when you hit any, let's say a big ball in the in your area or any place, so it will just bounce off. So this bouncing without releasing any energy, that is elastic, which is very simple. Questions, guys? Or yes, so this is the inelastic scattering. Actually, you have a very fast neutron. It will hit the nuclear here, and it will excite it, so it will be unstable. By having that, you will end up by releasing gamma ray. Okay, so this gamma ray has a certain energy for each element. So if you have oxygen, carbon, or calcium or silicon, every element, or let's say every one of these molecules, it will give us one, like a certain energy. By knowing this energy, we will measure how much we have of carbon, how much we have of oxygen, let's say. So this is the first one. And by the way, that one only happens when we have very high energy. So only at the few first microseconds. So the few first microseconds of the neutron, when it's released from the tool, this interaction will happen. Later, you will have only the others, which we will show later. So this is the peaks. So here, for example, showing like the peaks of carbon and the peaks of oxygen. You can quantify them and get the ratio of that. And by that, we know how much oil we have, or or water. This is the other one, which we call the capture. So what will happen actually? So when we emit the neutrons, it will go to many, let's say, collisions or interactions. After a certain time, just like shown here, it will be decay. The energy of that neutron will be decay till it reach the thermal neutron energy. So by reaching that thermal neutron, which is very low, then it will be captured by some molecule, by some elements, like for example, the chlorine, which has the highest in the environment, actually, the higher cross section, which we can think about it as if it is having higher probability to catch the neutrons. So the chlorine, whenever it's there, it will capture the neutron faster than any other element in that formation. So by capturing, you will end up also having a gamma ray again. So this gamma ray has also a certain energy for each element. By knowing its decay, we know what kind of element, and by knowing the decay, let's say ratio, we can have we can know this capture, and that is the sigma. So this is our sigma. So we have a sigma value for each element, for the oxygen, for the oil, for the oil, for the water, for the saline water, because it will be depending on the chlorine there. The last one, which is the neutron activation. So this is a little bit actually more interested to know. So this is, you can think about it here. I simplify it. So when there is a material is exposed to neutrons, these are the fast neutrons, as we explained earlier. There are some atoms that would like to absorb these neutrons. When these neutrons absorb, it will change these atoms to radioactive forms. Okay, and this radioactive forms then decay in a half-life. Every element has his own half-life, and that decay will give a gamma ray. And this gamma ray is also unique. It has a unique energy, and this gamma ray will show up after a time. It depends on the half-life. So, for example, here I'm showing the oxygen. So when the neutron hits the oxygen, it will change it. Let's say, yeah, you can see here we have 8 protons and 8 neutrons. The neutron will hit this oxygen to add a new neutron, and that will take out one of the protons. So by taking out a proton, actually, you will end up having different elements. So this will make it a new nitrogen instead of oxygen. But this would be decay very fast back to neutron, because this would be very excited and unstable. And by doing that, you will end up having again the oxygen, because it will get another neutron, and a beta, or let's say a beta particle or electron. So by having this, you will end up having the gamma ray. So this gamma ray will be measured and give you this activation. Let's say we call it the activation, so oxygen activation. Why do we need to know that? Because this will help us to, let's say, we can use the tool let's say, as to know the rate of production, especially when we have oil, water in that area. So we can measure the water rate at this area by knowing, the the time of decaying and the speed of the tool and so on. We can give after, we can give more details offline, inshallah. So here I'm showing some new products, or let's say new things that we use in our system recently. We can run Raptor in a memory mode. So this is invented especially for the offshore operation. So in the offshore, you need to have, it's not easy to get the unit in. It will be very, costly, and also the time consuming. Also the crew will be, higher there. So by inventing that, a memory Raptor that will enhance better. So it will give the exactly same measurement, but in a memory mode. We'll go to the specification of this memory also on the next few slides. So what value we get from this memory Raptor? You can reduce your, let's say, cost by 50%, more than 50 actually. It's very good to the environment, because you don't use any more of the units there. So you are reducing the gasoline you are using. So that's good to the environment. The operational cost as well. So you will have less people to work there, and so you will end up of reduction in the cost. Also, you will not be using like cranes, the personnel, like you will be having less risk in this measurement also. So that's why this memory Raptor was invented, and it is already operation in many locations in the world. So these are the specifications for this. Actually, the same modes, the same measurement exactly. However, we are using it in the let's say memory mode. this is the only one that I want to highlight here. We can go up to 20 hours of operation. So that's, I mean, you can have all of your measurement within this based on the battery life. And we can, I mean, the length, all of that will be with the gamma ray that you have, it's around 15 meter only. So the, and for the others, actually the same, the tool diameter is still the same with the same pressure and temperature rates that we are using. This is just a video just to show, I mean, a summary of this memory logging. So you can look at it. This was, let's go ahead. Have a question? Someone has a question?
Yeah. The question at the end, the lecture is finished? Lecture is
No,
finished?
not yet. No, not yet.
Okay,
Not
okay,
yet.
okay,
No
no
worries.
problem.
No worries.
Okay, you can answer maybe later. Okay.
No worries. No worries.
Mm.
Okay, so here are just the applications we mentioned as a mode actually, but we didn't go through the details of each application. So the most common applications here, the saturation, water and oil. This is mainly coming from the CO. We can have it in a saline water using the sigma and CO as well. When we have, let's say, unconventional reservoirs like a tight gas, you can use the Envision to quantify the gas or get the saturation of the gas. We can get a direct porosity measurement as well. From this activation, as we go through that, from the oxygen activation, it will help us to get the water flow log, so we can go the water flow rate. We can also calculate the salinity measurement. We can have it in the borehole actually. Oxygen activation, which can help us not only in the water flow logs, but also to quantify quantify oil. The water in the formation. Also, it will help us to see it in the borehole. So this will help us. Silica activation, especially when we have a gravel pack. So that will help us also. The emulated open hole measurements, so we can get all of the open hole measurements like the neutron porosity, density, resistivity, even the PEF. So all of that we can get it from the measurements of the Raptor by emulating these measurements. So it's not direct measurement, but we can somehow, by having some specific analysis, we get these measurements. So now we are moving to the case studies. I will show a few examples here. I try to pick, there are so many examples actually. I try to pick the most common one in our area here in the Middle East, instead of bringing others from around the world. So this is one of the examples that we run the Envision and CO in a single tubing. So we have 3.5 tubing, and we want to let's say see the contacts. So we have our own here is the open hole, and this is, let's say, the burst or the gas, the Envision, let's say the Envision envelope. I will explain it, and this is the CO envelope, and these are the saturations, and this is just the summary for all of it. What do we mean by the envelope here? So envelope is simply showing you a model of your, let's say, reservoir. So by modeling the reservoir, we can later, when we measure and log the reservoir, we can check where is our oil and water line in case of CO. And the gas here, we know the fluid and the gas. So here is our gas line, and this is our, let's say, fluid line. So and this is in the middle is our measurement actually, which comes from the tool. So this line and this line comes from the modeling, and the one in the middle comes from the tools. So by getting closer to the water line, or let's say, sorry, the fluid line, so it means that we don't have gas. When we are getting closer to the gas, we are having more gas. So similar to the lines that I showed you, the fan charts that I was showing, just I want to show it here like this, just like that, if you remember. So by having a big difference between the gas and water line, you will have better estimation of your saturation. So here, what we have actually, you can see the distance is high, so the certainty or the sensitivity is better, and the measurement is better. So this is showing us the gas and the fluid. Here we can have the difference between oil and water. By combining both of them, we will have the three-phase, like oil, water, and the gas. So this is the, you can see this one. I mean, the one behind showing you the old open hole saturation. However, this is the updated one. You can see the oil is only in this area, not in here anymore. So all swept, and the new oil water contact is here, and the gas is a little bit like it was maybe more in here. So now it is here. So this is the gas oil contact. So by combining the two modes, we can have a three-phase analysis. This is the same, but in a carbonate reservoir. So we have a carbonate, again, with the both modes here, the CO and the Envision. So here we are having, I mean, from the, you can see from the CO, here we are having very low porosity. So this is very tight compared to this area here at the top. Okay, so but still we can see it in the Envision, and you can see the difference is very high compared to the CO, the conventional measurement. And the good thing here, I'm trying to highlight, as I mentioned, like the two lines here coming from the model. Okay, so they don't know anything about the tool measurement, but you can see the tool is following these curves, and so just to show how sensitive is the measurement. So this is just showing the powerful of let's say measurement in this tool. So you can see here this quantifies, like from the Envision we can see there is a bit of gas in at the top of this reservoir, and we couldn't see it actually in the CO. So in the CO we can just see oil and water. Here we can see the difference between fluid and the gas. So by combining three of them, we can see the three-phase all together. This from Iraq, actually, this example. So we are having a reservoir, it is a sandstone, and it's actually a single barrier. You can see it's only 7-inch casing here with 8.5 bit size, and this is our tool. And we can see this is the open hole measurement here, showing us that we have oil in this area in the beginning, and now we have two measurements here, sigma and CO. So from the sigma, you can see we are showing only oil and very good oil saturation. However, by plotting the CO, we can see here we are having more of water. So let's say we can see 50% of oil compared to here, it's like almost 100% of oil. So the only reason is this water is fresh water. So because the fresh water and oil in sigma will be almost same value. So that's why it's not valid to measure, to let's say run only sigma in the freshwater environment. So you can see this area is swept and there is more of freshwater. Only this area you can see here, still the oil shown there, which is almost similar to the original oil saturation in the open hole. So you can see the zone 1 is unswept and the second one is mainly swept. This is, we call it a time-lapse monitoring. So we measure like to have two, to run the tool twice. Like here we, to monitor the reservoir, like we have run this tool in 2015 and 2019. And we can see the difference here. So you can easily tell the difference. You can see this is actually, this is a gas reservoir and we have only gas and water. So you can see this area was swept in the beginning. So we have the water up to here in 2015. However, in 2019, now it becomes even higher. So the gas, let's say water contact, water gas contact, let's say the gas water contact is become a little bit up after, let's say, 4 years. So that's what I mean by monitoring the reservoir. So this will help us. Actually, the model is the same. You can see it here, but the measurement is different. So the tool was measuring the gas up to here, but now it comes up to this depth. So this is actually, these are the let's say some of the examples. If you want also more examples, I can share it later after the presentation. If you need more of let's say gravel pack examples, or let's say the much more complicated environments as well, or very high. I have like examples for very high. I will show it actually later in the as papers. We have written many papers about it. You can go back to see it. Like we have done in a very like a huge, let's say high borehole size, like even more than 17-inch. I remember 17.5-inch borehole. So we still can get the measurement even within that size. So this is the summary actually, just to show what is the benefits of this tool. So it will help you to increase the production, of course, to manage the reservoir, as we shown the examples, like to monitor your reservoir, to see the updated contacts, either oil water contact or water gas or gas water contact, to also prevent your water encroachment, restore the missing open hole data sometimes, and to reduce also the cost, of course, as we mentioned in the memory mode. So these are the papers. Actually, I just mentioned a few of them. There are many. I can share later if you want. You can contact me. And yeah, we can have it later. I mean, in the saved video, you can go back to read more about it and to see many examples in this. So I think that's enough. I hope I didn't get longer. I think I am within the
Perfect on
time.
time. English time. Okay. So
Thank you. So yes, questions,
my
guys.
camera. Yes. Okay. My camera is not working again. Oh, so that was really informative and fruitful lecture. Thanks for your effort, Mr. Bilal. And we can start the Q&A section. There is some question in the chat box, but I see Mr. Sufyani raise his hand.
Yes.
Sufyan?
Yeah.
Maybe he raise it and go. Okay.
Maybe by mistake, yeah.
Yes. If you want to take the question in the chat box, if you can see them.
Let's see the first questions. Let's start from the top, actually. But, yeah. For measuring oil, which technology provides the most accurate results for measuring oil and water saturation, Envision, carbon, oxygen, CO, login, or sigma? Actually, we mentioned that in the slides. Maybe that was the beginning. You asked this question, but yes, you. Let me go better to that slide. So. It's better to explain it in the. So here is the chart. Okay, you can see it. Like if you have higher porosity, like even I mean, you can run all of them actually, but even sigma can give you a good results with the higher salinity and higher porosity. So sigma alone can give you this value. However, if you are uncertain of your salinity, or you have a fresh water, and let's say you have a good porosity, not very low, so carbon oxygen is good. You can combine it with sigma to get a better, let's say, to reduce your uncertainty. And vision, it's, let's say, specifically done for the gas. However, we can even get more beyond that. So you can get the saturation as well. However, in a tighter environment, like 3%, let's say 5%, up to, let's say, 15%. In this case, the better only to run this Envision. So the carbon, oxygen, or sigma will not work perfectly. I have seen actually carbon, oxygen in an environment with the 10%, but I mean, let's say statistics there is lower. However, we can still get a measurement, but not as run it with high porosity. So by knowing this, you can decide. I hope I answered this question. No comment. We can go to the next one. Okay, this one seems to be dependent on the level of saturation, if I am not wrong. Okay, this is how we can differentiate gas and light oil. Okay, this is a good question. So again, so the Envision actually, it's not based on the density only. So the gas compared to the light oil, it's further. I mean, let's say the molecules are further away from each other. So the lines between them, let's say, it's different. So the fan chart. So we can get, let's say, the difference between the gas and the fluid from the Envision, and from the CO we can get the oil and water. So at the end you will have three-phase analysis. And is there a minimum of porosity? That yes, this is the minimum porosity. Depends on the value. I mean, depends on which mode you are. In conventional reservoir, shale sandstone, then about that the tool cannot measure. Yeah, the same thing here. What does case hole neutron porosity from Raptor called? We call it emulated open hole curve. So still called neutron porosity, but emulated, like we call it emulation. So it's like it's not direct measurement, but it's kind of analytical that's done in the software to create these curves. It's not only the porosity, but also the others like resistivity, density, neutron. Okay, do you have any example or case study where Raptor been analyzed for spectroscopy? Okay. This is a good question actually. So City is asking if we have spectroscopy, let's say mineralogy in this tool. Actually, there is not direct measurement of mineralogy in this tool. However, we have some we call it neural analytical examples that we have that we are also similar to the emulation that we do for the open hole. We can somehow create some let's say equations and analytical measurements inside the software that we can end up of having this mineralogy. But is it a direct measurement? No. We have another tool which we usually combine it with them with the CR. We call it GSI. Maybe one of our team can provide it in the future. So that will give us more about the mineralogy. What is the point for having a gamma ray transmitter within the tool for the memory version? What are the other differences to consider telemetry only? Okay. For the first, I don't know if you mean that by having a second gamma ray, like we usually run 2 gamma rays to know, especially for the activation or to know the fluid production. So we need to have the second gamma ray. However, for the telemetry, the differences in the memory tool, we are having a battery there. And so this is the main difference in that tool. However, the size, the temperature, everything, the tool measurements are the same actually. Does the tool consider casing thickness like CBL tools, unlike the open hole? Let me read it again. Does the tool consider casing thickness?
Yeah, I believe he's asking the effect of casing and cement, okay, on the tool.
Yeah, of course. So for every, I just mentioned it very quickly because I cannot give all the details, but it's a good question. So for every well, we need, so what will happen? So if you have a reservoir and you want to log it, it's not just come on, bring the tool and let's log it. No, we need to model. First, we need to know your reservoir. We need to know your schematic diagram there. So what is the casing size? What is the, is it cemented? Is it good cement? What is the borehole size there? What kind of fluid you are having in the during the logging? So we need to all model that. So what you saw that when I show you the envelope, you can see the difference between the gas line or water line or whatever, oil or water. So the difference, this is all depends on the to, let's say, the environment you have there. So yes, everything is modeled. Where I reached does this. Okay. So Envision is equivalent to T3D from PNX. What is the added values compared to the competitors? Thanks. Okay, so yes, I showed you an example actually. I cannot go to the details of the competitors, but I can give you example, which I will go back again and compare them. Where was that? 1 second. Yeah, here. So this one. So the conventional, or let's say the competitors, most of our competitors they have 3 detectors. So these are the 3 detectors. Okay. So you have the source here, or let's say, yeah, the source, the generator, sorry. And you have 3 detectors here. So by comparing the 3 detectors, so let's say, let's have the measurement between only the proximal and the far. Here, what we have. So this is the dotted line below. So the dotted line below, here there is very narrow or short distance between them, between the gas line and the water line. So you will have a higher uncertainty when you have your data in between. However, when you have a further, so you will have better sensitivity and better estimation, especially I'm saying in the gas. So when you have gas, so you will quantify it more when you have a further, like the one here, we call it long detector. Yeah, we can. I mean, I cannot include it here in this session because it will be very long. So there is emulsion and there is emulation and the mineralogy that I was mentioning. So we can also get it from the neuro analysis. So maybe we can have that as like a different session in the future and compare it also to GSI.
So you can run this one in open
Okay.
hole. You can run
Yes.
this one in open hole
Yes.
for mineralogy?
Yes.
Ah,
Yes.
okay.
The GSI tool, yes, we can.
This one, like a version called GSI.
For the no for the CRE, it's made to be run in the case hole. However, it can be run in the open hole, but it's not preferred to. However, there is the GSI. We can run it in the open hole better.
Ah,
So,
okay.
Yes. Yeah.
Okay. So I believe the question is end. Okay. So I just have a few quick questions from my side. This is very actually interesting tool. Okay. Take Pulsed-Neutron to the next advanced level, actually. So regarding the CO delivery, CO interpretation, I believe it cannot be done with the operator house unless they have some kind of plugin or something. So the interpretation have to be done by Weatherford trained personnel, and they will give saturation and porosity from CO mode to operator house.
Yes. Exactly. Yeah.
Oh,
We
they
can. There are actually, I mean, build up Pythons, but it's not in our company. So there are some companies develop these kind of Python scripts, but however, we prefer to do it in-house because we need to use the model, yeah, and the analysis. Yes. But we are very transparent, so we can use it. We can do it in your desk. So this is done, yeah, so frequently.
Okay. And I saw there is a silica activation. Is this for what you call it, sand, gravel park or sand production?
Yes. Yeah, I mentioned that in the, yeah. We can.
Yeah,
I can show some examples as well. I have with me. We
yes.
can share it offline. Yes.
Okay. Okay. Not online. No problem. And regarding the porosity, I believe many people ask about this one. So the porosity is getting from this tool after Weatherford developed to be 5 sensors is getting more near to the open hole porosity in the unacid zone uh, or something, or still depend on you get the porosity from operator so you can start the interpretation.
Okay. So of course we need to have the open hole there. If you have it, I mean, in your reservoir, that will be better. So it will help us and better estimate the saturation. However, if we don't have it, we can still estimate it based on this analysis. And of course, there is some kind of uncertainty. I'm not sure
The
what is
porosity.
the level yet. Yeah, and in all of the measurements, not only the porosity, like we have
Okay.
like resistivity, we can also get it from this tool. We can get the density measurement. We can so there are some uncertainty there. I don't have the exact uncertainty percentage. I might get it from the team. Maybe we can share it also offline. However,
Okay.
yes. So to have the open
It's
hole
better to have it.
results,
Yes.
yeah, it will. Yeah, because you want to know the updated. So it's better to be. I mean, to know exact what was in the original there, and then you can better estimate what is updated actually. So this is the
Okay.
best scenario. However, if in many cases you have a missing, there are many cases actually, like you have a missing open hole data in this well and you want to run this tool, maybe you have an offset well to that well. It also will help. So bringing this offset well will help us to let's say reduce the uncertainty of these measurements when we get to know the saturation. Yeah.
Okay. And do you have like from your experience the effect of the acid? Like usually wells, it's not even all well. Like many of the wells in carbonate, they have been acid after a while many times. And this will distort all the formation, all the nearby porosity. So the open hole porosity actually will not be, but I saw some papers, they comparing like one open hole section, they acid it and they run again the open hole tool. It's totally like different story, become like a different thing for reading. So how usually take the acid effect if this like come by your desk or something?
Yeah, it's actually very nice and good challenge. However, I'm not sure if we have run this tool in such an environment. I may search more within our team, and I will get more details to that one. But it's very good. I already write it down, so we will
Yes,
for
I
sure. I
mean,
will search for it. Yes, this is really good.
yes,
Yes,
thank you.
because we are having it a lot. Yeah, but however,
Yes, like
we have cases like I'm not in this exact example, but we use it like let's say for the frac. Let's say frac.
pre and post, pre
Yeah,
and post.
especially yeah. You know, in now even so, it's usually in the US. You know, when you have like this
Shell,
let's say
shell
shale
reservoir?
oil, yeah, the shale reservoirs. So running CRE along with the NMR sometimes it will help a lot. So we have good examples as well. So that, but later they will use this acidizing whatever. So, but in the beginning, I mean, running it in the lime, I mean, the carbonate. Yes, I know it will do lots of
Very
changes.
challenging after
Yeah,
acid, yes.
yeah, but
Okay.
I don't know if we have examples. I will search for sure. I will have
Yes.
something in the globe. Yeah.
Yes. Yeah. Yeah, and my point is the porosity that come from open hole is not valid anymore after we do many acid job. Maybe only for the part that wasn't perforated. This is my point, you know.
Yeah, we mentioned like we can measure the porosity, like, but I
Yes.
want to see what is the difference. I don't know if you have
Yes.
examples. Yes, I'm sure it is
I
doable, but yeah,
yeah, I believe the porosity maybe from the new tool is better than the old one, because the old one is okay. So I like to, if there is no more question, okay, I believe the last question have been answered already. If there is any applications reference for CO2 monitoring, not CO. CO2 monitoring.
CO2. Yes, we are actually the same. This is the Envision. So CO2 is part of gas. So similar, it can be used for the steam, for the CO2. We have examples as well. So yes,
Okay.
it's good. Maybe I can share it also.
Okay. Okay. Thank you. And the depth of investigation, I saw you mention it in your presentation. Somebody opened. 1 second. I believe somebody have like a radio or something.
Someone can mute you. Maybe.
I'll mute. Okay, I believe it's have been muted. So I would like to thank you, Mr. Bilal, for your time and for your volunteering to support the technical activities and the Society of Petrophysicists and Hologonalists. Hopefully, we'll be in the future to be in touch for, as you mentioned, for this lithology application. Okay. Dr. Mohammed, any last word?
Yes, Mr. Mazen. Dear Mr. Bilal Shaheed, on behalf of SPWLA chapter in Iraq, we would like to express our sincere gratitude for your valuable presentation for today. Thank you for sharing your knowledge and experience. So, dear attendees, thank you for joining us in today's webinar, and we truly value your time, interest, and active participation. We also extend our deepest appreciation to the sponsors for their support in making the SPWLA Iraq chapter event a success. We wish you continued success and look forward to welcoming you again at our upcoming events. Thank you for joining us and have a wonderful day.
Thank you all. Mr. Bilal, any last words you want to say before we go?
Oh, thank you. It was really a pleasure to attend this session. So I'm also learning from you guys. So let's hope that we meet again, inshallah. And I will come back with some of the questions here and with the answers, inshallah, as well.
Inshallah.
Thank you very much.
Thanks for your effort, Mr. Bilal. Thank you, Dr. Mohammed, and thank for all the attendees. Okay, I will conclude.
Have a good day.
Have a good
Thank
day.
you.
Bye-bye.
Bye-bye. Bye-bye all.